Alright guys, we're gonna keep learning cryptography together, and let's go to the topic of today, which is the one-time pad. Okay, the one-time pad is the most secure way to encrypt a message. Unbreakable. Yes, I'm not lying. Obviously, it has some limitations, but we're gonna see that it's a truly secure way of encrypting something. And so to start this, to introduce one-time pad, we should go back to the Caesar cipher for a second, because we saw that the Caesar cipher was working by shifting. So if we have hello, and it was, let me make a little alphabet here, B, C, D, E, F, G, E, J, K, L, M, N, O, P, Q, R, S, T, U, P, X, Y, and Z. Okay, if we were doing a Caesar cipher, we would, and we have a key of 3, then we would shift everything by 3, right? And we saw that, again, hello, 1, 2, 3, it's gonna be K, and this is gonna be the E is gonna be 1, 2, 3, it's gonna be H, and then the L, 1, 2, 3 is gonna be OO, and the O is gonna be PQR. Core. So, what's the problem here? Again, we saw that the problem is that, for example, 2 letters in the ciphertext correspond to 2 letters in the plain text, and this is really bad because we can do this thing called frequency analysis, and also, obviously, if we have a bigger ciphertext, we can count the number of the H, you know, if this message was longer, the H's would be a lot, and therefore we know that the most common English, the most common letter in English word is E, and that's how we would get to the solution. We would break Caesar cipher. So let's fix the limitation of the Caesar cipher by introducing the one-time pad. So the one-time pad basically makes encrypting something secure because the key is no longer, like in the Caesar cipher, 3, but it's gonna be a longer key that shifts this letter randomly every time. So, let me check the notes. Okay, so how the one-time pad first is that first we have to come up with a key, with a pad, and this key can be, let's see, this is a key, this is a piece of paper, and the key has 4, 1, 7, 10, 1, 3, 5, 1, 2, 2, 7, 3, for example. Now this is gonna be our key. Actually, yeah, this is gonna be our key for the one-time pad. We have still the same plain text to encrypt, which is hello. Okay. And the way it works is that we need first of all to take this key and share it to the recipient of the message. So let's say that I have to send this encrypted hello to Bob, to Mr. Bob, which is usually used in every example of cryptography. This guy is Bob. First thing first, since this is a symmetric encryption algorithm, I need to get the keys to Bob. Now, and keep in mind this because we're gonna get back to this key delivery later, but I'm gonna drive to Bob's house and with my briefcase, and I'm gonna hand to Bob this piece of paper, okay? This piece of paper which is called the one-time pad, the key, okay, for the one-time pad. So Bob is gonna have a copy of this, okay? And I have a copy of this. That's me. That's me. Okay, we both have a copy of the key. All right, so how would I go about encrypting this message to Bob? So I would start with letter 1, and so position 0 and position 0 of both the key and the plain text, and I would do the same exact thing I did for the Caesar cipher, for example. So let's see, we're gonna shift H 4 times, so H is gonna be 1, 2, 3, 4, L. Okay, then 1. Okay, then that's it. Once we use this key, we discard it, okay? And so, actually, let me do this, which is a bit more clear. So this is gonna be my copy of the key, and this is gonna be Bob's copy of the key. You're gonna see why. 1, 7, 10, 1, 3, 5. 1, 2, 2, 7, 3. Okay, identical key. Perfect. He has this piece of paper. I have this piece of paper. Now, what I'm gonna do is I go by key, and I'm gonna substitute 1 by 1. So then E substitute with 1 becomes F. Okay, we throw away this. Now 7, L is going to be moved 7 times, so 1, 2, 3, 4, 5, 6, 7, S. Okay, and now next is going to be 10, so again L is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is V. Okay, and then 1, O is going to be shifted by 1, so P. Alright, now first thing that you should notice is that this double L, which was a pattern that you could spot in the Caesar cipher, you can spot that pattern here, right? You don't know that these two are the same letters of the ciphertext. So you really cannot do frequency analysis on this encryption method, right? You can't really get insights on the plain text. Why? Because we never repeat the same shift. In Caesar cipher, the key was 3, okay? And we encrypted everything by the same key, so we were repeating, right? And VGNR, same things. Maybe our key was 3274. We would repeat, so by 3, shift by 2, shift by 7, shift by 4, and then again shift again by 3. So you see, like, repeating the pattern that the key, encrypts for, that's a big problem. That's what allows attackers to break the cipher. But if we're using, just like here in the one-time pad, a different key, a different shifting for every part of the data we want to encrypt, now we're completely eliminating the possibility of one-time pad, and I can show you mathematically why. So again, no repetitive pattern and uniform frequency distribution in the ciphertext. These are completely random shifts every time. You can't really deduce much from this to get to this. Okay, now let me give you a math, a little bit of numbers on how this is hard to break. So in Caesar cipher, again, we were using a key of 3, and so we encrypted this, and it became, I forgot, K something. And so what we needed to do to break the Caesar cipher was just to try every possible key, right? Try with 1, try with 2, try with 3, right? Try 2, try with 3, etc. Until we find, start from the, let me just make this one so it's So this is OTP, and let's make a Caesar. So the Caesar will be again K, then remember it was H, yeah, H, and then L is 1, 2, 3, O, R, I think it was R, yeah, ta ta ta. So with Caesar, we just need to try first shift everything by 1, then we shift everything by 2. So if we shift back everything by 1, we get K, we get J, we get G, we get blah, blah, blah. If we shift everything by 2, we get I, we get F, and we get OO, we get MM. Still doesn't look right. So we try with this process of brute force, and we try all the possible shift of Caesar. When we try 3, that's when we get hello, and we're like, aha, I just decrypted your text. Now, why this is not possible to do with the how can I say, with the one-time pad? Because if you think about it, here, how many letters how many possible shifts are possible? 26, right? So we have 26 possibilities to find the right key. What does that number look like here? Let's think about it together. So here, I have, first of all, 26 chances to get right the first shift, but then I have another, I have to multiply by, this is like combinatorial theory, is that I also have to pick the right shift for the second letter. This is a times, okay, multiplication. And then for the third letter, guess what? I'll have to just guess what key was chosen, right? What of all the possible shifts. So I have another 26 chance. And then for the V, same thing. 26, and then 26, okay? So literally, I'll have to guess every time the right key for each shift, which is, I think this number is called factorial and is literally, I think it's around 12 million, right? 12 million. 12 million for only for a 5-letter sequence. So basically, if here you only, if for the Caesar cipher you had 26 possibility to choose from, here you have 12 million possibilities because you have to guess all the shifts right after a time. So it becomes computationally impossible, almost impossible to pick the right key that will decipher this message. So this is why the one-time is powerful. One-time pad is powerful because instead of decrypting everything by the same key, by the same shifting everything, by the substituting everything by the same shift, we're gonna randomly choose randomly. Yeah, we're gonna randomly. This was generated randomly. We're assuming this. We're gonna randomly shift it every time, and every time is different. Okay. So let me see. Oh, and just to give a little bit of history, this was created in late 19th century and it was used in World War II. So the generals or the people involved in the communication will share a pad with each other. Now, to conclude the example, I encrypted this, hello, using this one-time pad, okay? Now I'm gonna deliver this message to Bob, and I can even yell this to Bob. I can say this, the point of encryption is that the ciphertext can be transmitted in public to Bob. It doesn't need to be, you know, because nobody, no people in between, right? No people have no idea what this means, okay? And they'll have to guess a chance in 12 million to find the right combination of shifts to bring this back to the original plain text. Okay? ciphertext, plain text and ciphertext. Okay, very good. Now Bob receives this message, LFSBP. Okay, and he's gonna go through the same pad in order, because that's what we agreed before, that he's gonna use the same shifts to bring back. Obviously he's gonna shift, instead of shifting forward, which is the encryption, he's gonna shift backwards, so he's gonna do decryption, okay? So let's say he's gonna use this shift to get to L and this shift to get to L. Obviously he's gonna, and then he's gonna get to hello. He's gonna decrypt the message, okay? And again, if I want to tell Bob next, I want to see meet me at 25th Avenue, for example, very bad example, just to then I'll have to continue with this pad and shift this by 1 and shift this by 3 and shift this by 5, etc, etc. Obviously if I run out of keys, or if my key runs out of shifts, I cannot, I repeat, I cannot go back and reuse them, because then what happens? Then we're gonna have the Vigenère situations, we're gonna have a pattern, and so in the plain text, attackers can figure out patterns if you repeat the key. It's very important that each substitution is made with a random, you know, you don't know what I'm gonna shift next, and I'm not gonna use the same pattern, okay? So again, the more I'll have to share with him another pad. So what they would do in World War II is they would have a stack of pads, you know, numbered. And you know, as the message were coming, both parties were checking off and encrypting and decrypting with this method, okay? So I think it should be pretty clear the mechanism of the one-time pad. Again, very important to know that the key is never, that the key is as long as the ciphertext, right? Because the key to encrypt this was 1, 2, 3, 4, 5. The key to encrypt this was 4, 1, 7, 10, 1, okay? This was the key, okay? So the key has this, is the same length of the plain text, okay? Very important, if the key was shorter and we had to, at the fourth letter, go back to here, we lose the strong property of the one-time pad. We lose the uniform frequency distribution. That's what it is. Uniform frequency. There's a, you know, you can't really predict patterns using a key of the same length of the text. So we went over the fact that you have to destroy the key after Bob and me decrypt this message. We need to, you know, we finish the pad, we burn the pad, we burn it, we destroy it, so there's no trace of the key, and we do not reuse the same key. We do not repeat the pattern again. I think I repeated a lot of times now. So hopefully it's clear. Now, it seems perfect, right? We're able to create a ciphertext and send it over in the internet, shout it in the street, and only Bob will be able to break it, and no attacker, and the attacker have a crazy amount of difficult odds against them to break this. So it really is a perfect encryption, an unbreakable encryption method. Let's though talk about the limitation. Nothing is perfect, especially in the world of informatics. There's always a drawback, right? So the limitations are the following. So first of all, I don't know if you catch this detail before, but I had to drive to Bob. I had to drive physically and give Bob the pad with the secret. Right? This is a secret. I'm like, hey Bob, it's for you, and I make sure that nobody's watching, and only Bob has this paper. Now, what if Bob lived in another continent and I cannot give it to him physically? Why? I can't send him this by email. I can't send this by text message because the internet, the Wi-Fi network, everything is a non-secure channel of communication. You know, anybody can be in the middle of me and Bob in an internet connection and eavesdrop this key. And so if somebody else other than Bob has this key, then my encryption is broken and is not secure. Because encryption, you know, the base of encryption is that my message gets to you and only me and you are able to encrypt and decrypt. So, so one limitation is the key transmission, okay? We need to be able to give the key, the pad, to my recipient safely, okay, 100% safely. Then it's a limitation is the security of the key. Once I receive my key, my one-time pad, I need to make sure it stays safe. If I lose one sheet, or if I'm drinking coffee and I spill coffee and this letter becomes blurry and I cannot read it, then my whole, even if it's one little page in a whole stack of one-time pads, then the whole thing, well, maybe this is a bad example because it's the last one, but let's say I spill coffee and then this character becomes like ineligible, or the dog bites a piece of this away, right? If the dog bites a piece of this away, I'm screwed, because then what's the next key after this one? I lose the whole, you know, encryption. So the security of the key of the pad is a limitation, right? I need to guard and make sure it's safe. Third limitation is the length limitation. All right, length limitation. So as we saw here, to encrypt hello, we need a key of the same exact length, because if it's not of the same length, I'm gonna end up repeating and giving the attacker some basis to start cracking my plain text, sorry, ciphertext. And so, okay, no problem. 5 digits, 5 letters, 5 letters of the key, no problem. But what if we have to encrypt? Remember that now we're using letters and the alphabet, 0, 1, 2, 3, 4, 5, 6, 7, because it's simple for us humans to understand. But in a real software setting, this is going to be zeros and ones, right? And so the same logic applies, the same unity applies. If we have 1 terabyte of data, we're going to need 1 terabyte of key, right? So there is a length limitation. The key is always long as the message. You can use a small key to encrypt a lot of things. And so length is an issue. Let's see, can you exchange of the OTP? I think I'm repeating, so I already went over exchange of the pad, of the one-time pad is something very important, because it's the assumption. I said that this is the strongest encryption algorithm, assuming that, right? We're assuming that only me and Bob have the key, right? And now, last but not least, OTP. Randomness. Now, I think the book dedicates a separate chapter on randomness and computers, but I'm just gonna mention this now because it's very important as a limitation for the OTP, is that this key needs to be truly random. really, really, really random. And so, why? So let's say I generate this with a program like Excel or with a C function. We don't really achieve randomness, true randomness in computers, because computers are deterministic machines and they use math. And math is a very, you know, precise and set science. If we can't say to a computer, hey, make something random, computers are following instructions. And so what we end up in computers are these things called pseudorandom generators, which, you know, use some complicated math to get you a string of numbers, but it's never going to be true random. That means if the attacker is able to hack or figure out the pseudonumber generator that created this key, he will be able basically to guess what the next numbers are gonna be, which means our key is compromised, which means our encryption failed. So very important that this key is completely at random, right? So that the sequence of shifts cannot be predictable. And randomness, it's very hard to achieve, and that's why I put it in the limitations. And I think we basically went over. This is the one-time pad. This is what you need to know. I think these are the most important things. Again, hello, in this example we use letters, but these can be symbols, this can be bits, right? So in computers, what one-time pad would look like, and this is the example that the book mentioned, is that is the use of a thing called the XOR operation. So we have hello, let's say the letter H is an ASCII number, is a character number 26, and 26 in binary is 10011110. Guys, I really don't wanna, I'm too lazy to make the math and check if, but you get my point, right? And so now, if we have this, so this can be a plain text, right? And this is our computer treat data. They put it down in bits, and then they get a key of the same length. So let's say there's a key of 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, right? And so this is the plain text. And this is the key. These two are going to be combined again, bit by bit, like 1, 1, 1, 1, with an operation called XOR, exclusive OR. And XOR, if you're looking at this video, you should know what XOR is or bitwise operations are, but it's basically going to be like this. The resulting ciphertext is going to be this XOR with this one, which I think is, guys, I'm having a memory, exclusive OR. I'm forgetting, guys. If it was an AND, this would be 1. If it was an OR, this would be 1. Forgot XOR in this moment, but let's say 1, 1 XOR is 0, and then 0, 1, 1 is 1, etc., etc. You do the XOR operation to find the resulting bits, and then the bits are reconverted into a number, which might be, I don't know, 13, which might correspond to the letter L. And so that's how, you know, letter by letter, the computer would perform this encryption to get the resulting start finish, right? But again, guys, if XOR bitwise versus simply shifting letter, doesn't matter. It's an implementation detail. What matters is knowing that we have a process, which is the substitution, the bitwise operation, and then we have you know, the whole considerations that we did about having a key of a certain length and, you know, all the things we went over. So don't get stuck on the fact that, you know, the bits, the XOR, or the substitution. What you need to know of the one-time pad, and I think is important, is knowing all these process of sharing a key, having the same number, the key of the same length of the data, and the transmission of the key, and also very important to know the limitation of the one-time pad, because nothing is perfect. All right, I promise I'm gonna review the XOR. I'm gonna make sure don't come unprepared. Just slipping to my mind right now. And that's it. So one-time pad, the perfect way to encrypt something. Thank you for watching, and I'll see you for the next topic.